Okay, so in this tutorial, we're going to continue looking at more different kinds of graphs and how we can create them and various variations. There are so many nice graphs that you can make in data science that a lot of them, some of them you can make in Excel, but a lot of them, there's really great ones that you can't make in Excel. And then we're also going to look a little bit more deeply at JSON data, importing them, extracting data, the relationship between JSON and text strings, and doing some conversions between text and dictionaries and so forth. Again, the dictionary stuff, the JSON stuff, is more closely related to the lectures that we're doing in the rest of the class that you are not seeing. All right, so to begin with, we're going to import some packages. So pandas, numpy, seaborn, and matplotlib. So we've seen all of these packages before. Pandas is for our data frames. Numpy is for some calculations. Seaborn and matplotlib are for our plotting. And as in our previous tutorials, we are working with this employee data set that has two categorical variables disguised as numbers, and then the rest of these variables are numerical variables. Now we're going to look at some scatter plots, some kind of plots that you can compare two numerical variables to each other with. Now we've looked at some previous ways of calculating scatter plots, plotting them with the pyplot function directly from matplotlib. In this case, we're going to look at a relplot. We're also going to revisit the lmplot and the rugplot, which could also do similar things. Now, in our initial example, we're going to use this relplot function. This is nice because you can actually create lots of different kinds of graphs from some of these seaborn functions by simply changing the kind attribute. Again, if you're following along with your own data set, choose values that are numerical values for both x and y. So again, here we're going to create a scatter plot using this relplot function. And so this should be similar to graphs that we've seen from previous tutorials. So here's our annual salary, here's our age. And again, it does look similar to the graph that we had in a previous video. Now, I can also create a line graph from this same relplot function. Now, if you were to try to do a line graph of this data in Excel, Excel would try to connect the dots in the order that they were displayed in the file. And so what you would end up with is the sort of tangled yarn of chaos, as the ages are not in any sort of order in the original data set. And so it would actually just create a mess. Now, Python is a little smarter than that. So what seaborn is actually going to do is quite interesting. And so let's actually just look and see what it does. And then we can talk about exactly what happened. So if I run this cell, I get a graph that looks like this. So this is not that tangled yarn that you would expect to get from Excel, because it's not trying to connect the dots in order. Instead, it's treating this as essentially kind of like a time series graph. So it's trying to create a line connecting points in the order of age. But in many cases, there's more than one value at each of the age points. And so the line is actually plotting essentially the averages. So the line is calculating the average in each of the categories. When there's only one value, then there's no average to calculate. It's just the true value. But when there is more than one, it's essentially calculating an average and showing you the range of values at that age, and then just connecting the dots at the averages together. Now, obviously, this is quite chaotic. This data is definitely not designed to be plotted as a sort of an ordered variable. But if you have an ordered variable, even if you have multiple observations at each point, you will still get a much more comprehensible graph than what you would get out of Excel for the same data. So it's worth keeping this in mind because sometimes you do have data that is quite complicated. And at least you know that with seaborn, you can get a slightly more sensible graph out of it than you might get from some other types of graphing functions. Now, we've seen in previous videos the lmplot and the regplot, and so I'm just going to remind ourselves of what those do. Again, these are sort of the two standard graphs where you're trying to create a regression line with or without a scatter plot in the background. And again, lmplot is sort of the linear model plot, and regplot stands for regression plot. But again, these are ways of getting plots that compare two numerical variables against each other. So again, here is our reg plot with the regression line on it. We saw in a previous video, I can add the property scatter equals none if I want to take away the scatter. I could also color code these by other variables in my data set. And again, the reg plot is going to do something very, very similar. Now, another type of useful plot set in seaborn is the catplot. Now, what the catplot does is it is going to plot categorical variables, and you can use them to plot categorical variables, numerical variables by category. So think of comparative box plots or bar graphs, as we saw in a previous video with age. It'll calculate an average for the bar height. So that's the kind of thing that we're talking about here. So the default plot for catplot is essentially, it's technically a strip plot, or you can think of it kind of as a scatter plot with a little bit of jitter. So what it's doing, each of our categories, 0, 1, 2, 4, 6, 8, or 0, 2, 4, 6, 8, the education levels are plotted on the horizontal axis, and then the values of salary are plotted essentially as points above that. Now, they're not plotted literally vertically as they would be in a genuine scatter plot. Again, there's a little bit of wiggle in them to try to get you to see sort of more of the density of the points in each of the categories. So they're not plotted quite so much like literally on top of each other, which can disguise the number of values a little bit more. So some random jitter has been applied so that they're not literally right on top of the 4. There's a little bit off to the side so that you can see more of the points more easily. But the name for this is sometimes called a strip plot. And that's the default type of plot in the catplot function. Now, if we add the attribute kind, then we can force this into being other kinds of categorical plots that we've looked at before. So the bar graph. So we saw this from the bar plot function in a previous video. We get these bars for each of our categories. It calculates an error bar, which of course is larger for smaller data sets and smaller for larger data sets. And of course, the 0 category turns out it has a lot of variability in it. It's not only a small number of observations, but it also has a wide range of values in it. So that's similar as a result to the bar plot function. If we change this to box, then we're going to get a comparative box plot. So we'll get one box plot for each category for annual salary. So we had looked at a single box plot for one numerical data set before, and now we have a box plot that compares the new salaries in box plots across the different education levels. And again, we can see the plots of the extreme values. Now, the strip plot, as I noted, is the default, so that you can specify that, but that is the default type of graph if you don't specify kind at all. But you can also change the orientation of your plots. So in this case, I've changed orient to H, so for horizontal. The default orientation is obviously vertical because that's what we've been seeing, but I can change the orientation to horizontal so that the category X is on the vertical axis, and in this case, the salaries are on the horizontal axis. These values are quite large, and you can see the numbers kind of run together at this size. So this is not my preferred orientation for this, but it is something that you can do, and you can actually do this to other kinds of graphs. So if we were to change this to box or to bar, then we would be able to create horizontal bars or horizontal box plots as well. Now, some other kinds of graphs that you definitely can't make at all in Excel are swarm plots, violin plots, and point plots. Now, a swarm plot is going to be somewhat similar to the strip plot, except they're going to, instead of just having random jitter, they are going to stretch out values that are very similar to each other and kind of stack them sideways, the way that you would with some kind of a dot plot. And the advantage here is you can see where points are clustered kind of in the middle of the distribution. So where is the fattest part of your distribution? Where do all the points kind of build up on each other? So the strip plot is a little bit random, and so things do kind of fall on top of each other, but you get a little bit better view than like literally vertical lines where everything is stacking up. But in this case, everything is meant to not overlap at all. And so they will just keep getting stacked outward so that the dots don't overlap each other directly. And you can see, again, more sort of where the fat parts of the distribution are. Where do the values tend to cluster? And we can turn that into a smooth distribution curve by using the violin plot. So if I run that, then again, this swarm plot basically is replicated here, except that the distribution curves are now smooth. So rather than plotting individual points, you kind of have this box plot type structure in the middle, and then this distribution curve sort of floating around it. That's why people think it looks like a violin. And then the point plot is kind of a variation on the bar graph. So if we go back to our bar graph up here, the bar graph is created from these averages in each of the categories and these error bars. And then in the bar graph, bars are created underneath them. But in the point plot, only the point at the averages are going to be plotted, and then there will be lines connecting each of the points. It will include error bars by default. So again, in our bar graph, these were bars that were both about the same height. And again, their average values are both plotted here. The error bars are still here, but now instead of bars under each of them, they're just points, and then we connect them to each other. So this graph is a little bit more stark. If you're not accustomed to reading it, it can be a little weird. Bar graphs are much more common, but it's basically just another kind of graph that's conveying the same information that was in the bar graph to begin with, just a different sort of display. Now, the one variable numerical data that we were doing histograms and box plots for earlier, there is also a seaborn plot called a displot, so distribution plot, for these one variable numerical types. And they also have different attributes that we can look at in order to get different kinds of graphs out of them. So we had plotted the histogram before in the matplotlib function, the pyplot, and here we're going to layer it in with the seaborn. And so again, this is for annual salary from our data set. If you remember the pair plot from a previous video, down in the little corner where annual salaries histogram was plotted, the shape of this is a little more compact in that example, but it should be somewhat similar, not exactly symmetric, with a little bit of a tail to the right. Now, if I change this kind from histogram to KDE, I'm going to get that the KDE stands for kernel density plot. I'm going to get a smooth curve for the shape of my distribution. So again, I can see, it's in the middle, it looks like it's not too bad, but then I do have this sort of weird right tail. Now, one thing to keep in mind about the density plot and the histogram is that by default, the histogram is plotting in counts, and the density plot is counting in proportions of the total. And so the scales are quite different. We're going to look later at putting plots on top of each other. And so you want to be careful about that with the histogram and the density plot without doing further modifications. The scales are quite different. And so if you plot them on the same graph, you're not going to be able to see the density plot at all relative to the counts. Now, the ECDF is the empirical cumulative distribution function. So this is a way of looking at how many, what percentage of the data is below a particular salary, for instance. And so it's going to accumulate up to 100% on this side, on the right side, and 0% on the start on the left side. So this is our person that's making the least amount of money. Everybody makes less than them. And then as you accumulate additional salaries, different values, you get a larger and larger percentage of the people who are making salaries that are at or below that value, cumulative distribution, until you get to the top where the very last person accounts for 100% of people are making at or below their salary. So sometimes this is useful for seeing, again, how the properties accumulate, whether sometimes that can give you information about anomalies in the data if it's not a smooth distribution. And then a rug plot is another kind of plot that also does, essentially it does hash marks for any time there's an individual value. And by itself, it's a weird graph because it's basically empty. And it just does, again, one sort of tick mark for every value in the data set. Rug plots by themselves are not usually done, but you will see them in combination with density plots because of that disconnect between the count and the proportion from our histogram to our density plot. Those are more difficult to plot together. So to get them some information about the original values in the data set, along with that nice smooth density curve, combinations of displot and rug plot can sometimes strike that little bit of a balance. And this is usually the context in which rug plots are actually used, is in combination with these density plots. So if I run this, you'll see that here's my density plot, and the rug plot at the bottom indicates that there are some values that are out here, and there's a lot of values that are in the middle here, and then there's some stray values that tick out toward the side. And so again, they're trying to impose a smooth curve on these observations. Now, when we're doing comparisons of two variables to each other, we originally just looked at like scatter plots and line plots. But there are other ways that we can do more complex analyses graphically, and that is with a joint plot. And joint plots are very popular in data science because they have an interior plot which compares the two variables to each other, and then they have plots on the margins which are also going to add additional information about individual values in the data set. Now, I'm going to take out this hue equals education for a moment, just so that we can look at what the default joint plot looks like if you're just comparing age and salary. And then we'll add in the color of education so that you can see how that changes the graph. So for the initial joint plot, the default without any color coding is essentially you have a scatter plot. This is our age versus annual salary scatter plot that we've seen a couple times. But in the margins here, on the opposite margin for annual salary, you have a histogram of annual salary. Now, in this case, the right skew is actually toward the top. So be careful with the orientation here. And then the top opposite the age is the histogram of age. So there's a lot of information going on here. We have individual plots of individual numerical values and the combination of how they relate to each other. Now I can make this more complicated by putting back in hue is education. Now hue is education has 5 values. That's going to color the scatter plot. It's also going to change what happens on the margins. And so when you do this, it doesn't do histograms by default anymore. It does density curves. They're a little easier to see relative to each other, but then the scatter plot in the middle is going to also be color coded by education. So our annual salary with that color coding. Now, 5 categories is a lot. 2 categories is a little bit easier to read. So again, color coded by gender, and then the density plots, because there are fewer of them, they are just a little bit easier to understand what's happening. Now, I can do the same joint plot and change the kind to hist. And so if I have a combination like hue equals education, where I'm getting density plots on the margins, maybe I'd like to get histograms instead. Well, if I do this, this is going to also change what's happening in the interior of my graph. So again, if I run this, again, this is kind set to hist. I do get histograms by color stacked up against each other, but it also changes my interior here to a 2-dimensional histogram. So again, depending on the kind of data that you have, this may or may not be appropriate. It may or not give you the kind of information that you want. And typically the color coding in here is going to be indicative of the counts, the number of values, as well as the categories. So this can be quite complicated when you're doing lots of different values at the same time. If we take out the hue equals education, then again, the color coding here is not colored by type of education. It's being colored by how many observations are in the bins. And so when you have this additional hue data, it is a little bit more difficult to interpret because you have the education and the count sort of layered on top of each other. Again, this is just with kind equals hist without the hue. And then finally, this is the default with the scatter plot and the combination histograms that we looked at earlier. Now, you can, if you want, there is one additional setting that you can try. We saw with these previous examples up here that there is a density curve. Well, our density curve in the one variable case was KDE. What happens if we set kind equals to KDE instead of hist? So you get a density plot on the margins, but your scatter plot is now replaced with a contour plot. So that's another option that you can use for these joint plot functions. So depending on the kind of information that you're trying to convey, you have a bunch of different options: two-dimensional histograms, scatter plots, or these density functions. All right, now for this next discussion, we're going to continue talking a little bit about dictionaries and in the context of JSON data frames. Now, you're first going to need to install the JSON package. You should do this normally from the Anaconda prompt, so from outside your Jupyter Notebook, but you can do it from inside Jupyter Notebook as long as you save your file and restart the kernel after you do the installation. So you would do something like pip install JSON, and then it would install this as a package that you can then run. If pip doesn't work, you can also do conda install. For installing packages, I recommend looking at the Anaconda documentation for how to do package installation. But this is going to be the first package we've encountered that is not a built-in package. And so you will need to install this before you can run it. Now I'm going to import it now because I have installed it. And this was our dictionary that we just looked at at the end of the last video. So we have our name value pairs, and it's surrounded by curly brackets. And so now this is saved in our memory as a dictionary. Now, we saw another example in the last video, at the end of the last video. We're also going to look at another example here of how to essentially use the JSON package to turn text, plain text, into a dictionary, because JSON files are essentially just text files. So when you load in a JSON file, you're just going to get a text string. So for my example, I've created a string variable that has the structure of a dictionary, but it's enclosed inside single quotation marks, so that Python is initially going to treat this as a string. So similar to the kind of things that you would get if you imported a JSON file, you would just get a text string. And then what it's going to do is this JSON loads function is going to turn my text string into a dictionary. So similar to the example we had above. So I'm going to run this. Now, if I want to look at it, then I just call the variable name and it will display. So notice here that there's no quotation marks anymore around this because it's no longer a string. It has now been converted to a dictionary. If I were to run just person, then it prints with the string quotation marks around it to tell me this is just a text string. It has no structure except that string structure. But once I've converted it to the dictionary using the JSON package, it now has a dictionary structure. Those quotation marks have gone away when I print it out. Now I can extract information from my dictionary. For instance, if I want the languages information from my dictionary, then I treat that essentially like a column as I would sort of in a pandas data frame. I specify the name of the attribute and not the value. So here I want to pull the languages values out of my dictionary. And so the values will then print my list, English and French. If I were to change this languages to name, then it would print Bob. Now, if you have a JSON file and you want to load it into Panda, into Python, again, you would want to specify where that file is located. So again, ideally, I would recommend putting it in the file in the same folder where you are running your Jupyter Notebook, so you don't have to worry about the path to the file, just the file name. And then with this with open function, you can save it as essentially, again, a text string as F, it's a text variable, and then use the json.load function that we were just looking at to convert that text string into a data dictionary. Now, you can also extract information from a dictionary into a JSON file because JSON files are just text documents. So what this JSON dumps property will do is it will actually dump your dictionary content into a plain text string. And so likewise, there are ways to save this then as a JSON file. So if I run this and then I look at the results, remember my dictionary originally when I printed it, if I go back here, it's printed with curly brackets to start because it's a dictionary. But after dumping it, it now prints as a text string with the single quotes around it. And so this is how I would then export that into a file. I first convert it to a text string, and then I save that text into a file if I want to export it as a JSON file.